Hey, physics. So we're going to go over this assignment number 1 for wave model. I think it's like assignment number 3 in total. So the speed of light found by Michelson's experiment here to be 2.9 times 10 to the 8. So not quite the proper speed of light, but that's the speed that he got. If the two hills of his experiment are 20 kilometers apart, what's the frequency of the 8-sided rotating mirror that he has there? Okay. So the formula that we use for this year, we developed in one of our other classes or other videos there for lessons, is C is equal to 2 times D. And the reason we have to have 2 times D because the light has to travel there and back. Okay, that makes sense. Times the number of mirrors that we have, so which is 8, times the frequency will equal the speed of light. So what we know is we know the speed of light. So I'm just going to rearrange this. Well, the speed of light that we have here. So this is C here. This is N. And they give us the D here. So I'm just going to rearrange this for F here. So I'm going to divide it by, or divide the 2dN over to the other side here. And we're going to get 2.9 times 10 to the 8 meters per second. I'm going to divide that all by 2 times the 20,000. Make sure to change that into meters and the 8 sides. And what we're going to get here, because it's meters per second, we're going to get per second is our answer. And I'm going to get 906. Yeah, 3 sig digs here. 906 hertz, because it's per second. Now the key is that this is per second, so that means the next question here, because it says per hour, the frequency, that is my frequency, because it's revolutions per something. Since this is per hour, I'm going to change this to per second. Okay? So it seems like quite a bit, but that's a whole hour of it rotating. That's a lot of turns that can happen in an hour. So I'm going to change this to per second by dividing by 3,600. Okay? So this is a much nicer number. If I divide it by 3,600, that's the same logic as kilometers per hour. Why do we divide by 3,600 in that situation? Follows that same logic. Oops, sorry. It ends up being 519.444 hertz. Okay, so I'm dividing by 3,600 because that's how many seconds are in an hour. Okay, so we know the frequency. We know the hills are 35,000 meters apart. Okay, we're looking for the speed of light, and we know the number of sides in the mirror here is, again, is an 8-sided mirror. So this is just going to be 2dNF. So 2 times your 35,000 times the 8 times the frequency in hertz. If you look at the units, that's going to be meters per second. So that does end up in speed times 8 times. So we get, well, we get that same number from the previous question here. So we have 2.91. I'll go 3 sig digs times 10 to the 8 meters per second. Looking pretty good. All right, so our radio wave is now traveling across Calgary at a total distance of 40 kilometers. How long does this take? So if the speed of light, or the speed of all EMR is the speed of light here, I could say that V is equal to D over T, and if I want to know how long it's going to take, I'm just going to go D divided by V. I'm going to use this formula because light travels at a constant speed. So it's traveling at 40,000, or so it's going to travel 40,000 meters, and it's going to be at 3 times 10 to the power of 8. So I'm going to use the accepted value from our data booklet there. Not the numbers from the previous questions. So use this one. So we get 1.3333 times 10 to the negative 4 seconds. So I could just put that in 3 sig digs here. If you want to, you can change it to milliseconds. So I can divide it by 10 to the negative 3. I get 0.133 milliseconds. I want to change it to microseconds. I can do it again. Move my decimal place 3 times, and I get 133 microseconds. Sounds pretty cool. How far does a beam of light travel in 1 millisecond? Looks like 1 millisecond. Yes, this is 1 millisecond. I don't want to change it to that because why would you? I'm just going to use that formula up there. V times t is equal to d. I know the speed of light is 3 times 10 to the 8 meters per second. I know my time in seconds, which is good. So I'm just going to multiply those two things together. Travels quite far, 1 millisecond. Travels 3. Oh, sorry, it's 3. I messed up my calculation here. Just double check that. 300,000 meters, so 3.00 times 10 to the 5 meters. If I want to put this in kilometers, this would be 300 kilometers in 1 millisecond. Cool. What's the frequency of red light? So if I know red light's frequency here is 10 to the 14, 6 times 10 to the 14 hertz, what we know about from one of Maxwell's predictions is that EMR behaves with the universal wave formula, where it says speed is equal to f times lambda. And if I'm just going to say it's traveling through air, we're going to make that assumption. This is just going to be the speed of light. And then I'm going to rearrange this for wavelength. Okay, so 3 times 10 to the 8 meters per second. I'm going to divide it by my hertz here. Times 10 to the 14 hertz. That's per second as well, so they're going to cancel out the per seconds. And let's just type this in my calculator here. And I'm going to get 5.00 times 10 to the negative 7 meters. Now, I usually don't like this in meters. So what I'm going to do is I'm going to change this into nanometers. It's kind of more on the orangey side of red light, it looks like. So what I'm going to do to change that to nanometers, I'm going to divide by 10 to the negative 9, because that's how many meters are in every nanometer. You can just look up on your formula sheet for that. The reason we're using nanometers here is because that makes this a nice number. So this ends up being 500 nanometers. There you go. So that's how you do those questions on the assignment. Similar questions are going to be on the quiz. I'll see you in the next video. Bye.